Okay, 2.26, mathematically speaking, is a pretty trivial problem. It's really easy to actually solve this, but conceptually it's a little bit more tricky, and Griffiths actually sort of goes into a rant sort of about the problems with doing a Fourier transform of a Dirac delta. I am also going to go into detail about this, so for now I'm just going to ignore this and sort of do the problem first. So we're asked to find the Fourier transform of delta x. We have sort of the formula from Plancherel's theorem. So we know, first off, that f of x is just equal to a Dirac delta of x. So the Fourier transform, f of k, is going to equal 1 over the square root of 2 pi times the integral from negative infinity to positive infinity of the Dirac delta of x times e to the negative ikx dx. Immediately, Dirac deltas pull out functions at specific values. In this case, it's going to pull out e to the negative ikx at x equals to 0. So this is going to be 1 over square root of 2 pi e to the 0 times the integral from negative infinity to positive infinity of the Dirac delta of x dx. This, by definition, is just equal to 1, and this is also equal to 1. So the Fourier transform of the Dirac delta is just equal to 1 over square root of 2 pi. Then we can reverse this and say the reverse Fourier transform is going to be, Dirac delta of x, which is f of x right here, is then, according to this formula, equal to 1 over the square root of 2 pi times the integral from negative infinity to positive infinity of f of k, which we just found is 1 over square root of 2 pi, times e to the ikx dk. Now, immediately we pull out the 1 over square root of 2 pi. We get 1 over 2 pi times the integral from negative infinity to positive infinity of e to the ikx dk. And if we look, this is exactly what Griffiths said we should get. So that's the actual problem done. Now we can sort of go on to this second part, more of a conceptual exercise, talking about why this is problematic. So the reason why, instantly, hopefully you see this instantly, and sort of the problem here is that this is not a true statement. This does not equal a Dirac delta, because if we think about what a Dirac delta is supposed to equal, a Dirac delta is defined to equal infinite when x is equal to 0, and 0 when x doesn't equal 0. So if we look at this integral, well, at x equals 0, this is just going to be equal to 1. So at x equals 0, it does indeed equal infinity. At x equals 0, this is in fact true. However, when x doesn't equal 0, this integral is going to be 1 over 2 pi times the integral from negative infinity to infinity. And if we invoke Euler's identity, we're going to get cosine kx plus I sine kx dk, where x is some positive or negative number that isn't 0. And the problem is that this is now just an oscillating function. And the problem with oscillating functions, especially when you take infinite integrals of them, is that their integrals don't exist. They don't converge ever, because the integral never flattens out infinitely far away. So as you take this integral, you have to keep on adding and subtracting, and the resulting sort of integral is going to oscillate up and down as you go out farther and farther. So because of that, sort of taking infinite integrals of oscillating functions that go out forever to infinity doesn't make sense. This is undefined. Now our requirement is that when x doesn't equal 0, the resulting integral has to equal 0. This integral does not equal 0. It's undefined. So because of that, automatically, this definition is wrong. Now, the reason why this happens is because the delta function, as sort of Griffiths says here, doesn't really meet the requirements to undergo a Fourier transform. And sort of the requirement is that the function that you're transforming, f of x, must be square integrable to undergo a Fourier transform. What does this mean? What this means is that the integral from negative infinity to positive infinity of the magnitude of f of x squared dx must be finite. So it can't go to infinity, it can't diverge, it must converge to some finite number. the integral of the Dirac delta on its own, the integral of Dirac delta of x dx is indeed finite. This is equal to 1. However, it doesn't really make sense to take the square or the magnitude squared of something like a Dirac delta. And sort of the reason why is because the Dirac delta isn't actually a proper valid function. Sort of remember back at the very start when we introduced delta functions, one of the things I mentioned was that a Dirac delta is sort of an artificial construct. It's a definition. You know, we invented a Dirac delta with this definition in mind, that it equals infinity when x equals to 0, and it equals 0 when x is non-zero. Obviously, this does not meet the requirements for a function. It's discontinuous. It jumps from 0 to infinity instantaneously as it goes from a non-zero value to 0. So this isn't a real function, and because of that, it's not something that sort of applying a square integrable. It's not something that we can apply a magnitude squared onto, because it's not a function in the first place. Sort of trying to take the magnitude squared of Dirac delta of x is sort of analogous to sort of saying something like dividing a constant by 0. The result is, in technical terms, undefined, because you can't do it. A Dirac delta isn't really a function. It's a mathematical construct. You can't perform operations like magnitude squares on it like you can do for standard functions. More generally, Fourier transforms require well-behaved functions. More concretely, they require functions that generally are continuous and have derivatives that are also generally continuous. So a good way to sort of say this is that most of the time when you take Fourier transforms, you're doing it for smooth functions. Smooth functions are basically functions that are infinitely differentiable, and their derivatives are all very nicely behaved. There's no discontinuities or anything. And because of the fact that the Dirac delta is this artificial creation that isn't actually a real function, it's not considered a quote-unquote well-behaved function, and because of that, it can't be transformed. So because of that, we run into sort of this issue of sort of the Fourier transform that we get being very obviously incorrect.